We're going to map its energy on one axis, the reaction coordinate on this axis, or reaction progress, and it just starts out somewhere with our conjugated diene plus our acid. Some energy value, relative energy value 0. And as we add a proton to this, it's a very high energy process as it has some transition state. There's some sort of transition state up here. And we get to our carbocation, and we know that there's resonance for this particular carbocation. So this is a resonance pair. But this species is very reactive. It's much higher in energy than where we start. This is a stable molecule, not a stable molecule. And actually, if we were to look at this a little bit more carefully, this secondary form, the form where the plus charge is on the secondary position, this looks a little bit better than this one. These two are distributing this charge between these two positions, the 2 position and the 4 position, the secondary allylic carbocation, the primary allylic carbocation. One of these two is a little bit more stable than the other one. Think about which one of these two forms is a little bit more stable than the other one. As this traverses the next energy landscape here, as this carbocation traverses this next energy landscape, I'm going to erase this here, and so are you. These diagrams don't have to be perfect by any means. The key points that I want to illustrate will be self-evident when we put them there. What I want to do is down here at this point, I want to put in the 1,2 addition product. Okay, so we're going to put some energy level here. It's actually more stable than where we started. That's where I goofed. I drew this line a little bit higher. So this product is actually more stable than here. Okay, this is the 1,2 addition product. And if we go along this particular pathway here, we're using the secondary allylic carbocation. The 1,2 addition product was favored at low temperature. This was favored at low temperature. And this is the transition state for the secondary form. This point right here is the transition state to get us from here to here. If we're using the primary form of the carbocation, it's much, much higher in energy to use this particular one. But the final resting point I'm just going to redraw this just a little bit. Don't worry. I'll take time and explain these things very, very slowly, but we're going to draw the 1,2 addition product, or the 1,4 addition product below the 1,2 addition product. The 1,4 addition product is lower in energy than the 1,2 addition product, and we're going to explain this phenomenon very, very shortly. This one is favored at high temperature. Okay, this diagram you're not going to have to redraw. Okay, but we're going to explain these 2 important points about kinetic control and thermodynamic control using this diagram. At low temperature, minus 80 degrees, we make this allylic carbocation, but in going from the allylic carbocation to the 1,2 product or the 1,4 product, there are different transition states. They have different energies. And at low temperature, we don't have enough energy to get over this barrier to form the 1,4 product very much. The smaller energy barrier is favored at low temperature. Favorite at low temperature, not much energy. This particular product that results from the 1,4 is formed as the minor product. This is at the major product. At high temperature, the only thing that determines the outcome of the reaction is the stability of these two products. And it turns out this is more stable than this one. This particular alkene is more stable than this one. So even though these transition state energies are very, very different, at high temperature we could get over this one or this one. And the higher one is actually more stable in the end because this particular product is more stable. You might recall from general chemistry that these processes are reversible. So if we have enough energy to make it over this particular barrier, even if we make this particular 1,2 product, the reaction could reverse and then come over the taller barrier and make this product. So this particular product is more stable or more thermodynamically stable. This particular product is more easily formed. And that's illustrated in the transition state. This one's harder to make, but in the end it's more stable. And we're going to talk about that particular issue right now. I don't think we actually got to the alkene stability trend. The alkene stability trend will become important next week. So when we talk about elimination reactions, which we're a ways away from, we're going to learn about this alkene stability trend. But in short, tetrasubstituted alkenes, so this is a tetra substituted. This is a tetrasubstituted alkene. It's more stable than a tri-substituted alkene. This is tri-substituted. It has three things that aren't hydrogen. That's more stable thermodynamically than a di-substituted alkene. I'll draw a trans one for our lecture today. And that's more stable than a mono-substituted alkene, etc. So this is tetrasubstituted, tri-substituted, di-substituted, and mono-substituted. And we're going to learn next week that the more carbons we put on an alkene, the more stable it is. So maybe that came a little bit too late in our discussion, but for the time being, this is a di-substituted alkene. And this is a mono-substituted alkene. And this particular arrangement of atoms, if we compare these two molecules directly, this one actually has a lower energy than this one. These two are constitutional isomers. But constitutional isomers have many different properties. They have different names, different behaviors. And it turns out that di-substituted alkenes will be more stable energetically. So at high temperature, we favor the more stable product. At low temperature, we have access to the more stable transition state or lower energy transition state. For us, mere mortals, in this fast, rapid-paced summer class, we just simply have to keep in mind that the 1,2 product is a kinetic product. It's very easy to make it. It's the one we're most familiar with. Maybe that's the mnemonic you can use. We've been making these all last week. The 1,4 product involves resonance. To get there involves some extra heat. So this is the main slide that's the most important part for you to digest, along with how to do these two mechanisms, how to use resonance. This particular energetic diagram, I'm not going to ask you to recreate it. I'm asking you to study it enough so that you know the rationale or reason why a product is called a kinetic product. It has a small activation energy and easily accessible transition state, but the product it forms isn't the most stable. Thermodynamic products are based on the energy of the final molecules, this versus this. This one's represented by this blue line. This one's represented by this red line. This is lower in energy and more stable. So difference here has to do with kinetics. Lower is better. Difference here has to do with thermodynamics. Lower is better. Okay? That's really what you have to walk away from this particular slide. Again, I know it's confusing. complicated. There's better pictures in the textbooks for us to do, but by drawing it, I think we get a better appreciation of it, and that's why I take time every semester with students to actually draw these things out, think about them a little bit, and work with them in that sense.